Apa Itu Rekursi. Ever looked into two mirrors facing each other? It seems endless, right? That's like understanding recursion. So, what is recursion? It's when a function calls itself to tackle complex problems by breaking them down into smaller ones. Recursion has two main components, the base case, which stops the recursion, and the recursive case, which keeps it going. Let's see a fun example, calculating the factorial of a number. Factorial of n, written as n, is defined as follows. If n equals 1, return 1. Otherwise, return n times factorial of n minus 1. Now, let's go through the steps of factorial 4. Factorial 4 equals 4 times factorial 3. Next, factorial 3 equals 3 times factorial 2, and so on. Finally, we reach factorial 1 equals 1. And we unwind all the way back to get 4 times 3 times 2 times 1 equals 24. But what if we remove the base case? Let's find out what happens. If we remove it, the function keeps calling itself endlessly, leading to an infinite loop or even a Stack Overflow error. So, the base case is critical to tell recursion when to stop. To wrap it up, recursion is a powerful programming technique, but use caution. Without a base case, it never halts. By grasping this concept, you can tackle complex problems elegantly. Now, have you noticed that sequence of numbers that seem to have a pattern? Like 1, 1, 2, 3, 5, 8. This pattern is described mathematically, and it's called a recurrence relation. A recurrence relation is a formula that expresses values in a sequence based on previous terms. The Fibonacci sequence is the most famous example of a recurrence relation. The formula goes, Fn equals Fn1 plus Fn2, starting with the initial values, F0 equals 0 and F1 equals 1. This means F2 equals F1 plus F0, which gives us 1, and F3 equals F2 plus F1, resulting in 2. See, it just continues, F4 equals F3 plus F2 and so forth. Recurrence relations and recursion in programming are tightly linked. When you create a recursive function, you're implementing a recurrence relation in code. Recurrence relation bridges the gap between repeating patterns and mathematical formulas. Knowing this helps you understand sequences like Fibonacci and allows you to create algorithms for various problems. Imagine you have a sequence where each number depends on the previous one. That's a recurrence relation. Let's kick off with a straightforward example. For instance, an equals 2 times an1 with an initial value of a 0 equals 3. Our task? Find the general form of this sequence. First step, let's calculate a few initial terms to see the pattern. A 1 equals 2 times a 0, which results in 6. Next, a 2 equals 2 times a 1, leading to 12. Then, a 3 equals 2 times a 2, where we get 24. And a 4 equals 2 times a 3, that gives us 48. Now, let's observe, a 0 equals 3, a 1 equals 3 times 2, a 2 equals 3 times 2 squared. This leads us to the general form, an equals 3 times 2 raised to the power of n. This is the pattern we've discovered. By using substitution or iteration, we can solve simple recurrence relations just by observing initial terms. No complex formulas needed, just watch for the pattern. Next up, have you seen a sequence like this? 1, 1, 1, 1. What if we could change this series into a mathematical function? That's the idea behind generating functions. Generating functions are mathematical tools that transform sequences into algebraic functions. Take the sequence 1, 1, 1, 1. The generating function looks like this: fx equals 1 plus x squared plus x cubed, and so on. Surprisingly, this is a geometric series and has a closed form. Fx equals 1 divided by 1 minus x, for vertical bar x vertical bar less than 1. So, this infinite series can be represented with just one simple function. With generating functions, we can store information about sequences in an algebraic form. Think of it as the DNA of the sequence, concise, rich, and ripe for further analysis. In this video, we've just scratched the surface. Stay tuned for more on how to solve problems with generating functions. We've learned a lot: recursion, recurrence relations, and generating functions. But how do all these connect? Let's look at the big picture. Recursion is a way of thinking, breaking down problems into smaller versions of themselves. We express this mathematically with recurrence relations, and we analyze it further with generating functions.